is Mr. Laurent Simon from the Engineering High School of Enserbe in Bordeaux. Please come to the stage.
Another.
Hello, everybody. Thanks for the invitation. So what I would like to present you today is what kind of AI we may build for critical system like railway systems. So in fact, AI, despite the fact that in the recent years, for many people, AI is exclusively machine learning systems. In fact, AI is much more broader than that. And in fact, there are two kinds of AI. They are called System 1 and System 2. System 1 is more suited to tasks where you want to think fast. So it's more related to what we call intuition for ourselves. There, in the System 1 set of problems, we traditionally use machine learning techniques. For instance, if you want to design an algorithm that make a robot walk, then you have no idea of how you walk yourself. So you cannot design an algorithm to do that by yourself. So you design a system that learns by itself how to walk. So the System 1 is more like machine learning stuff, where you want to perceive, you want to detect if this is a cat or a dog. You want to find patterns in a large amount of data. Okay, so in fact, you want to find correlations. System 2 is more like symbolic AI. So it's called old AI because it was developed in the 70s, and it's more related to when you think slowly. When you want to solve a problem like a puzzle, you need to design a strategy, and in fact, you can have some introspection of the way you are solving the problem. And this AI is more about reasoning. So you want to design a system that can think. Thinking meaning reason on some data. Okay. So System 1, you want to detect correlation, and System 2, you want to reason. This is why it's also called AI. In fact, System 2 is very important because this is where, for instance, you may find causalities in your data. Machine learning cannot find causalities. They just find correlation, and what we want to build a big AI is more to be able to find causalities between events. Okay. So here I will just show you two cases of System 2 and System 1. The first illustration is a success story of AI for railway problems. Okay. This success story is based on System 2, so it's more like reasoning. So if we want to reason, this is symbolic AI, you need to have some rule for reasoning. The rules that we will use is a very old rule that was formalized like more 2,000 years ago by Aristotle himself. It's more like you have facts, so facts are true or false. And if you know that fact A implies fact B, and you know that fact B implies fact C, then you can deduce that fact A implies C. This is very simple. Okay? It looks like a trivial reasoning system. But besides the fact that this is very trivial, very simple, this is a logic we use to prove very complex system. Like if we want to do model verification, we want to do formal proof of complex system, this is exactly the kind of logic we are using in our tools. In propositional logic, all the rules that are on the left are written by symbols on the right. Like A implies B is written by what we call a clause, not A or B, meaning that either A must be false or B must be true. Okay, and the deduction mechanism rule is called resolution. Okay, this is just propositional logic, and so some notations. I have some technical slides just to change in your day. I mean, to make it look like more scientific presentation. So we are dealing with propositional logic formula. On the top left corner, you have such kind of formulas that we are dealing with. Like you say, x1 must be false, or x2 must be false, or x3 must be true. And you must have x3 to false, and you must have x1 to true, or x2 to true. And what kind of problem are we asking ourselves on this kind of formula? We are just trying to find a solution to this formula. A solution is just an assignment of the variables to true or false that can evaluate this logic formula to true. So for instance, if we set x1 to false, then not x1 is true. This is why it's green. And then the first line, it's a clause. The first line is true because you have at least one element that is true. The second line is true also because x3 is false. Okay, so it looks like a puzzle. I mean, you just want to find a solution to a problem. But this problem, I mean, if you can do it very efficiently, your life is in danger. Okay, this problem is one of the main problems in computer science. It's related to many, many other problems. And in fact, it's an archetypical problems that is hard to solve in practice. It's equivalent to attack a crypto code, okay, somehow. And so you have some notation and so on. Okay. So what kind of problem can we handle with that? And the relationship with railway problems. In fact, we can encode some problems of reachability. The reachability problem, it's with the schema on the right. So you start on the green point, and you want to check if the red point can be reachable in any number of steps. Okay, so on this problem is very simple, but of course, in practice, the kind of reachability problems we are dealing with have much more states than there are particles in the universe. Okay, so it's a little bit more complicated to check. And for instance, how can we translate such kind of problems into SAT? I'll just show you a small examples. Here, it's just an example of an additioner. Okay, you just want to add 1 to a binary encoding. Okay, so at the input of this +1 stuff, there are the bits A and B. For instance, if you send 0, 0, you will add 1, so the A will be 1. And if you have 1, 0, you add 1, then you will output 0, 1. And if you enter 0, 1, you will output 1, 1, and so on. So it's just a 1-bit additioner. Okay, A is a lower bit in the binary notation. Okay, so this is a problem. And here, we just want to check if there is some state that is reachable. Okay. Okay. So, in fact, this formula that I showed will encode an automaton. Okay. And the problem will be, can we start with some state, and by unrolling the automaton, can we reach something, the right state at some point? The relationship with the railways will be that you will modelize your problems, like an interlocking station, and you want to see if there is some bad states that you can reach with your protocol. Okay, so you have a protocol. This is the transition function. Okay, that say if I am in this state, then I can open the door, and I am in this state now, and so on and so on. And you want to check if something bad happens. Okay, so you can translate this transition function into propositional logic. This one-bit additioner, I can encode it in a propositional logic formula. Okay, it's a little bit technical, but it's not so hard. So you say the output of A is just a negation of A, as we have seen, and the output of B is just the XOR of A and B. And for instance, in this illustration, I just want to check if the state 1, 1 is reachable from the state 0, 0. It's obvious. Okay, we have seen it in the chain, but once again, remember that we want to address problems with a number of states that is completely incredible. Okay, so how can we do that? We just unroll the transition. So we just say, okay, my first state is 0, 0. Okay, I'm starting with the state 0, 0, the initial state of my automaton. And then I say, if I start with the state 0, 0, t is a transition function, I can go to the state 1. A state 1 is designed exactly by instantiating the transition function from 0 to 1. And I do the same from 1 to 2. In fact, I unroll my automaton with the logical formula. And at the end, I just check my property. I say my property, my byte property is 1, 1. And I say, do I have A2 and B2 at the same time? Or do I have A0 and B0 or A1 and B1? Meaning that can I reach the state 1, 1 after the first transition, the second transition, or the third transition? And this is what I obtain is a propositional logic. Okay, so my initial problem, my initial puzzle, can be used in this example to check the reachability of an automaton in practice. Okay, this was just the technical part of the talk. And in addition, so I'm working in the SAT field, so I'm designing SAT solvers that can solve this kind of problems. And in fact, it's amazing how fast they are. They can solve problems with millions of variables. And once again, in theory, we cannot do that. But in practice, we can do that. And they can find a solution in a space, in the search space, where the universe is very small. I mean, the search space of our solvers is amazingly much more important than the size of the universe. Okay. And why it's very important also is at the end of the computation, when the SAT solvers say, yes, you can reach the bad states, or no, you cannot reach the bad states, the SAT solver can give you a proof. The proof can be quite large. I mean, it can be like terabytes of proof, okay, of resolution steps. But you can check it with a very simple algorithm that is proved by itself. Okay? And this was a success story for railway system in the 90s. Some complicated interlocking systems were proved to be safe by this kind of approach. And we are currently trying to help, like RATP, SNCF, to prove that the design of some stations are safe. Okay, so we just want to say if the train is here and the train is here, and if I open, then there is this happen, and you don't want to have any crash at the end. And it's proved, and you have an actual proof on it. Okay. I said that I will talk a little bit about machine learning. Okay. So machine learning is something that can advise you something. So you have a big amount of data. So this is not the same approach. It's not about reasoning. You take data, you learn something about data, and then you make recommendation. So you have a big computer that worked for hours, and then the big computer says, you have to change the wheels now. Do you trust it or not? You have millions of dollars. Everybody say yes, because the performance of the computer is better than a specialist. Okay, look at this specialist. You have 90% of performance. This computer is 95. It's better. So, but what if instead of a computer, it's a pigeon that say change the wheels now? Why do I say that? Okay, this is an example of an experiment made a few years ago. And the problem was to detect malicious cells in medical samples. Okay, so they were giving this kind of pictures to specialists, and specialists had to rank if there is a problem or not with the image. Okay, and they designed a machine learning approach that was beating specialists. So everybody say, okay, use this instead of specialist. Okay, but what was this machine learning stuff? It was pigeons. They just trained pigeons to detect if the pictures was pictures of ill person or a good, not ill person. Sorry for my English. Okay, so yes, that's good. So the problem now is that if you have a doctor, and the doctor asks a pigeon to know if you are sick or not, can you trust it? No. But here it's exactly the same. I mean, the pigeons shown much better performance than human specialists, and this is exactly the same that we have with computers now. In fact, everybody wants its ML decision system. I want to have ML to say to do something, and in fact, they are very good when it's okay to have an error. This is very important. This is the first point. The second point is that, in fact, you cannot trust them because ML systems are like pigeons. I mean, they don't understand what they are doing. The doctor, when he says you are ill, you have something bad, I mean, he understands the impact for you, not the pigeons. And in fact, we need to build something special. Like artificial intelligence, we need to build artificial trust. We cannot trust in an automated system the same way which we trust someone. Okay. And okay, no, I'll skip that. And I'm just going for my conclusion. I'm respecting the time. So trustworthy AI is a new field. And it's very complicated because all the machine learning area, they don't care about the trust. They just care about the precision. And the precision is not sufficient. So we need a paradigm shift in the machine learning community. We need to take the trust into account. In fact, from the beginning, if we want to deploy this kind of system. So for maintenance system, in fact, system 2, so reasoning system, are used, for instance, to give you an optimal plan for putting the train into reparation stuff and so on. I mean, you have an optimal reparation plan. But system 1 are still good for detecting patterns of failures. So in fact, they are used for predictive maintenance, where in fact, if you have an error, I mean, if you just take a piece of your train and you put it in reparation, it's okay if it was not already bad. Okay, the error is okay. So the main problem in the AI community is how to take the both of the two approach, system 1 and system 2, but it's something too complicated for the next 20 years, I think. But we are working on that. Okay.
Well, thank you very much for your nice presentation.
Okay, thank you.